This week we're going to continue our lecture on the analysis of control system. And if you remember at the when we look at the lecture that we had last week, we were studying the general response, the time response of first order systems, and we have used what we call the notions of poles and zeros in order to be able to identify the time response of a first order system. So in continuation of that, what we're going to do today is we're going to study the time response now. Instead of first order system, we're going to study the time response of a second order systems. So at the end of this today's lecture, today's lecture is going to be divided into two parts. The first part resembled what we have seen in last week's lecture, so studying the time response using what we call poles and zeros, right? So in this chapter, at the end of this particular lecture, you will be able, what I hope that you can achieve, that you'll be able to determine the time response of a second order control system using poles and zero. So now it's for second order systems. So what is a second order system? Second order system is basically a system with, if you remember in the first order systems, a first order system has a particular form or a standard form. If we can write them, if I can write them, it is basically in the form of, so this is for first order, yeah? So for first order system, the standard form or the general form of the transfer function would be A equal to G equals to, so GS equals to A over S plus A. So what we call as first order is basically when we have the poles, when we have only one pole. So the poles here is at minus A, right? So when the polynomial at the denominator of your transfer function, so this is your transfer function GS, right? When the denominator of your transfer function is basically in the order of 1, because the poles, there's only one poles, that's what we call a first order system. So understanding that, second order system is basically a system when the polynomial at your, so a transfer function can always be written as the numerator, I'll call as ns over denominator ds. So when we have the denominator is a function of a second order function, right, then you will have what we call a system of second order, where you have two poles in the transfer function, right? So that's the difference. So if you look at here, so I've scribbled something over the transfer function. So the general form of the transfer function would be, if I get my pointer back, so the general transfer function now, instead of having like in first order system A over S plus A, now the general transfer function would be B over S squared plus AS plus B. So the polynomial that you have here is, the higher order of the polynomial is S squared, right? And the polynomial can be written in standard form as S squared plus AS plus B. So this particular polynomial, if you want to find the root, alright, so because finding the poles is equivalent to finding the root of the polynomial, you would find two poles or two roots of the polynomial of S squared plus AS plus B. So this is the general form of a second order transfer function or second order system. We will be using this general form just like in previous chapter, and this general form will serve us in identifying the position of the poles on our S-plane. So in second order time response, basically there are several categories of time response. So what do I mean by several categories of time response? In order to understand that, let's go back a bit, look at the first order time response. In first order time response, all the time response looks alike. So if you remember the first order time response, when we studied the criteria of performance of it, the time response looked like this, right? When we have a general form of the transfer function gs as a over s plus a, and we find the poles, so the poles equals to minus a, as a function of the value of a, the form of this time response could change. So for example, we remember that if we want to find the time constant of tc equals to 1 over a. So if a, the position of the poles change, for example, is a is larger, then tc will be lower, or if a is lower, then the time constant will be larger. So what happened is it changed the form of your time response. It changed whether it can be a very responsive system or very slow system, but the form are still the same. It is a first order curve. So this is what we call a first order curve, right? So now what's the difference with a second order time response? In second order time response, we could have different categories of time response. It will not just be a time response that looks like this. It will have several categories of time response. And again, just like in first order time response, these several categories of time response that we're going to study here, so this is the point that we're going to study, particularly in this video lecture, it will depends also on the position of your poles. So position of your poles, or pole positions. So a slight revision, a small revision or reminder on poles position. So poles position, what are poles position? Poles position is when you find the root of your polynomial. So again, gs, your transfer function, can always be written as a polynomial on numerator divided by a polynomial on denominator. For example, in first order system, this is the polynomial of the denominator. If you find the roots of the polynomial in the denominator, this is basically your poles, right? And your poles, once you find your pole, what you need to do is to plot your poles. This should be automatic after this. When you find your poles, what you should do is plot your poles on what we call S-plane. So we've done this in previous chapter, but we revise again. What is S-plane? S-plane is basically a plane, a two-dimensional plane with two axes. Therefore, the first axis, x-axis, is the axis that we call sigma, and the second axis, y-axis, is what we call the j omega axis. So sigma axis represent the real number of your poles, the real component of your poles, and j omega represents the complex part or complex component of your poles. So if you remember, this is a polynomial. When you find a root can be a real number, or a root can also be a complex number. And in function of the position of your poles in this S-plane, the criteria of time response in second order system will change, right? Will change. So let's look in this particular slide the first type of second order time response, right? So I'll change to a pointer. So in this first category, what we're going to look at is what we call an overdamped time response. So what is an overdamped time response? So let's take an example of this particular transfer function. So this transfer function is written as 9 over s squared plus 9s plus 9, right? And in order to study a transfer function, what we do is we excite it with an input. And again, just like in first order, in order to study the behavior of a system, we inject into it an input of step. So an input of step, if you remember in previous lecture, in frequential domain, an input of step will become 1 over s. So what we'll do is we'll try to find or evaluate cs when we have an input of a step 1 over s. So our transfer function is 9 over s squared plus 9s over 9. So what do we need to do now? So we will use the position of poles in order to evaluate the time response, right? So that's what we call finding solution by by inspection. Finding solution by inspection means finding the position of the poles. So if you remember, solution by inspection means finding the poles. So finding the poles, what does it mean to find the poles? Finding the poles mean finding the roots of the polynomial or in the denominator, right? So let's find the root of the polynomial on denominator. If you want to find the root of a second, so this polynomial is basically a polynomial of second order system, second order polynomial. That's why we have now a second order time response. So I think you are very familiar with this formula. This formula allows you to find the two roots of a second order polynomial, right? So in order to do so, what you need to do is to plug in the value into the formula. So the formula is basically minus b plus minus square root of b squared minus 4ac over 2a. So what is a, what is b, what is c? So if we look at the polynomial, so you have a is the coefficient in front of s squared, right? So a is 1, b is the coefficient in front of s, b is 9, and c is the coefficient in front of the last term, which is also 9, right? So with a1, b9, and c9, you will plug into the formula, and you'll find out that the two poles are, so here are the two poles. We find two poles of the polynomial. The first pole is at minus 7.854, and the second pole is at minus 1.146. So now we have found the two poles. So as I mentioned just now, the thing that you need to do automatically after finding the pole is to plot the poles on your S-plane. So if we plot the pole on S-plane, so now there's a bit of dribbles on it. So we can see that here you have a j omega axis, here you have a sigma axis. But are there any use of the j omega axis? If we look into the poles are, both of them are real number. There are no complex component into the number. So both of the poles are situated on the sigma axis. So the first pole, sigma 1, is this minus 7.854, and the second pole, sigma 2, is at minus 1.146. So a remark that we can see is that both two poles, so the two poles are situated first on sigma axis, and they are both on the left side of the sigma axis. So this is the point 0 of the sigma axis. Both of the poles are located on the left hand side of the 0 of sigma axis, right? So the next thing that we would do is to find the general solution. So it's solution by inspection. So in general solution, what we would do to find the time response is basically we will do the partial fraction, right? So it's partial fraction that we do. So 9 over s squared plus 9s plus 9 can also be written as 9 over, so a second order transfer function can be written. So this is now in finding, when you find the, let's go a step back. So when you want to find the time response, what we're finding is basically the time response is CT. So in order to find CT, it is basically the inverse Laplace of CS. So we have to find CS. So what is CS? CS is, if you remember, CS is the product of RS, your input, multiplied by your transfer function GS. So RS is 1 over S, so that's where we have this 1 over S, and then our transfer function is the polynomial. So the polynomial can now be written as 9 over, so our polynomial is basically the product of S plus sigma 1 multiplied by S plus sigma 2. Sigma 1 and sigma 2 being the poles of our transfer function, right? Because we know that once you find the pole, this also means that now it can be written as S plus sigma 1 multiplied by S plus sigma 2. So this is also equals to our polynomial of s squared plus 9s plus 9, right? So now it's written in this form. When we have this form, what we can do is we can do partial fraction. So we have three terms in the denominator of our output. The first one is s, second one is s plus sigma 1, and the third one is s plus sigma 2. So we'll have three terms in our response CS, and when we look at these three terms, we can directly identify the time response by looking at the inverse Laplace of each terms. So the inverse Laplace of the first term k1 over s, we know is a constant k1, but the inverse Laplace of the second and the third term, the terms are s plus a pole sigma 1 and s plus another pole sigma 2. So this will introduce the exponential part, and they are by inspection, they are basically minus k2 exponential minus sigma 1 t and minus k3 exponential minus sigma 2 t, right? So this is the general form of the time response of this kind of second order transfer function. So let's see if we have this. What we will do next is basically find the coefficient of k1, k2 and k3 in your partial fraction. So we will not do again partial fraction in this part. I'll let you do the partial fraction. So if you do the partial fraction, we will find the final equation is basically k1 equals to 1, k2 equals to this coefficient 0.171, and k3 equals to 1.171. So at the end, this is our final time response, and when we plot it, it will look the curve will look like this, right? The curve will look like this. So this is what we call an overdamped time response. So what is the characteristics of overdamped time response? An overdamped time response looks a bit like the first order time response, but the main criteria that we need to let me have a pen or a highlighter. So an overdamped time response, the main criteria is that your sigma 1 and sigma 2, your two poles, are located on the left hand side of the S-plane. So if you have your poles located, both of them on the left hand side of your S-plane, then you will have what we call an overdamped time response, and the time response will look like this. So that's for overdamped time response. The second type of second order time response is what we call as underdamped time response. So again, the characteristic or the type of the second order time response depend heavily or depend solely on the position of the poles. So if you remember in the previous slide, position of the poles depends therefore on the denominator of your transfer function. So here let's take an example of a different transfer function. So now this transfer function in the second type of time response, what is that we call underdamped time response. This is an example of it. So let's imagine we have 9 over s squared plus 2s plus 9. So the thing that we want to do is to find the position of the poles and try to from the position of the poles try to identify the time response of this transfer function or this system. Again, we use the same formula to find out the position of the poles. So position of the poles meaning we have to find the roots of the polynomial that we have on the denominator. So it's still the same formula, but now instead of having b, which was previously equal to 1, now we have a coefficient 2 in front of this of the second term s. So now our b is 2. So what have changed? If we calculate the position of the poles, we found out that now we don't have any more a real component in terms of the roots. So our roots now is sigma 1 minus 1 plus j square root of 8 and sigma 2 minus 1 minus j square root of 8. So we have this complex component of j square root of 8, right? So where does these components come from? It comes from the terms inside the square root, so b square minus 4ac. If you have the terms inside, so this is just a revision of complex number, right? So if you have the terms inside the square root which is negative, then it means you have complex terms, right? So because the definition of a complex number, if you want, if you revise a bit, so the definition of j, a complex number, is basically square root of minus 1, right? So now if we calculate the let me get back to my laser pointer. So now if we want to write them in a simplified form, it can be written as poles sigma 1 and 2, they are at minus 1 plus minus j square root of 8. So the first one is minus 1 plus j square root of 8, right? And the second one is minus 1 minus j square root of 8 here. So it can be written as these terms. So there are two poles, there are not one poles, there are two poles, poles 1 and poles 2, sigma 1 and sigma 2. The real number are the same, it's at minus 1, and the complex number are now basically one is the opposite of the other. One is at j square root of 8 and another one is minus j square root of 8. So this can be written as minus sigma d plus minus j omega n, with a sigma d being 1 and omega n being square root of 8. So what do we need to do now is to plot it on our s-plane. So this is the plot of the poles on the s-plane. Again, we remind that s-plane is a two-dimensional plane with the x-axis being the real component of your poles and the y-axis, or called j omega, is the complex component of your poles. So now the real component is minus 1 and the complex component is square root of 8. There's one at plus square root of 8 and another one at minus square root of 8. So here we have our position of poles. The first one, sigma 1. So if I go back to my pen, so sigma 1, which is minus 1 plus j square root of 8, it is found over here. And second pole, sigma 2, minus 1 minus j square root of 8, are found here. So what are the difference with the position of the poles of the overdamped system that we've seen in previous slide? In previous slide, in the overdamped system, the poles are both on the sigma axis, right? But now the characteristics is that the poles are, so the poles in the underdamped time response, they are still both on the left hand side. So they are both on the left hand side of the sigma axis of the point 0. They're both on the left hand side, but now they are not in the axis of sigma. They have a component of j omega. They have j omega component, right? So what is the difference in terms of time response? So let's look at the time response. In order to find the time response, so we are skipping a lot of steps here, but they are basically the same steps. The steps are basically, you have to find CS, which is RS multiplied by GS, and then you also have to find, therefore, once you write this, it is 1 over S multiplied by your transfer function. So your transfer function now is 9 over, so you have two terms. So you have sigma 1 plus, you have S plus sigma 1 and S plus sigma 2. So sigma 1 and sigma 2 being these values that we have found just now. So if you do partial fraction and inverse Laplace, so the next step is basically partial fraction and then inverse Laplace, you'll find out that the time response CT can be written as this equation, right? It can be written as this equation. So the general solution will look like CT equals to a coefficient A, exponent minus sigma dt. So what is minus sigma d? Sigma d is the sigma d that you found over here. So sigma d is basically, in this case, is minus, sigma d is 1. So minus sigma d is minus 1. Cosinus omega d minus phi. So omega d, what is omega d? Omega d is basically this omega n. So it is square root of 8. And phi, what is phi? Phi is basically a phase shift that we found on the phase shift of sinusoidal sinusoidal waveform. So at the end, what we have, if we plot the graph, if we write if you do the partial fraction, the inverse and the inverse Laplace, we find that Ct in particular for this transfer function will be equal to minus 1 minus exponential minus t, all this term. So at the end we become this term, 1 minus 1.06 exponential minus t cosinus square root of 8t minus 19.47 degrees. So so the graph will looks like this. So what's the difference with the previous graph? The previous graph, if I can have a pen, in previous graph what we had was something that resembles to first order system without no oscillations. But now what we are remarking, what we can remark is there is a small undulation or oscillation that we can observe at the beginning of the time response. So this oscillation is basically the thing that's being presented by j omega. So omega is what we call a pulsation in radian per second. So that pulsation is being presented by this j omega term and can be identified in the time response by this sort of undulation, right? So if we look here, basically we have cosinus square root of 8. The square root of 8 is the j omega term. This term is basically the term that gives us this particular undulation. And so if we have a transfer function, now you know what we can use as properties in the coming exercises of problem that you have. You have a transfer function that have a poles that have both that can be written in this form. So it's minus sigma d plus minus j omega n. You can therefore write directly write your time response as in this equation, a general solution in this red rectangle. So to summarize, in an underdamped time response, where we have a transfer function, such transfer function, where when we calculate the position of the poles, we have the poles, both of them at the left hand side of our sigma axis, and both of them are basically an image of the other with a component of j omega. The time response can be written as this function Ct equals to a constant multiplied by exponent minus sigma dt multiplied by cosinus omega d minus phi. So if you look into previous slide, you'll know how to calculate phi. Omega d is our omega here, square root of 8, right? And sigma d is our real component, which is minus 1. Therefore, we can plot, if we plot the graph of this time response, we will end up with a curve of this form. So to summarize a bit, in a curve of this form, a curve in an underdamped time response have two components. The first one is what we call the exponential decay part, and the second one is the sinusoidal oscillation. So the exponential decay part. So the exponential decay part is basically the envelope of your time response. If we plot an envelope like the curve that we have traced in blue here, this envelope shows an exponentially decaying amplitude. So this decay is basically the part that's being presented by the real component sigma, this sigma, and this sinusoidal which have a pulsation or a frequency. This pulsation is being presented by the complex part of our poles, which is the j omega. So if we increase, for example, if we increase or decrease the value of the real component, it will change the form of your exponential decay, It will change the form of your exponential decay. And if you change the value of your omega d, if you increase or decrease omega d, what will happen is it will change the frequency of your oscillation. It will change the frequency of your oscillation. So there's we have two hands here. We have two parameters that can be played here. The first one is the real value, which so the real value affects the exponential decay, and then the j omega will affect the frequency of our oscillation. And now let's go to the next category of time response, the third one. So the first one, if we recap a bit, the first one is what we call overdamped system. The second one is what we call underdamped system, and now we are at the third category of second order time response, is what we call undamped time response. So this is a transfer function that will give us a time response that is undamped. So imagine we have transfer function of 9 over s squared plus 9. So the first thing that we want to do is to find the poles of this transfer function. So if you calculate the poles, we would find out that the poles are both at plus minus j3. So when you look at these poles, what happened is both poles only have complex component, and they don't have the sigma or real component. The real components are 0, and the complex component are at plus 3 and minus 3. So if you plot it on our S-plane, we have the two poles exactly on, we have the two poles which are plotted on the axis of j omega, and in the axis of sigma, basically they are at position 0, right? So what does this mean? If we look at the previous slide, from the conclusion of the previous slide, j omega is the component that will give us somehow will let us predict on the ondulation of the system, and the sigma component will give us a prediction on the decay, exponential decay of the time response. So now the decay is 0. If we look at the sigma component, both poles have a sigma of 0. So we have 0 decay, and we have an ondulation of basically of sigma equals to 3, right? So first we go to the general solution. So you can take this directly. The general solution is Ct equals to a cosinus omega minus phi. So omega being our omega that we found in our poles, which are 3. So if we plot the graph, we'll see that now Ct equals, for example, for this particular solution, for this particular transfer function, Ct is 1 minus cosinus 3t, right? So we see that in terms of ondulation, we have cosinus 3t. So it means that we have an omega of 3 that correspond to an ondulation of 3 radian per second, right? And then in terms of, let's look in terms of decay. So if we look at decay, we have 0 decay. What does it mean to have 0 decay? It means that the amplitude of our time response will not decay. It will not go towards 0. So it is maintained constant. When it is maintained constant, it means that our response will not go toward a steady state value. So what does it mean by steady state value? So by now you know what it means, a steady state value. So in first order time response, or in the previous two categories of second order time response, after a certain times t, the response will always goes toward a certain steady state value. So we have a finite value. But now what happens is, if you look at the values, the curve keeps on oscillating, and there is no finite values. There is an average values, but there are no final values. So when there are no finite final values, that means that we have zero decay. Right? So next time when you find that you have a poles that only have complex number, where the position of the poles are located only on j omega axis and has no real number, it means you have a purely sine wave signal, sine wave output, right? So no decay for an undamped time response. Well, that basically that's why it's called undamped, because there are no damping at all, and therefore the sine wave keep on oscillating without any final value. So here we comes to the last and the fourth category of second order time response, is what we call critically damped time response, right? Critically damped. What does it mean by critically damped? So let's take an example of a transfer function. Now we have at the denominator. Now you know that the part that's important to look at is the denominator, because this is the part that will give us the position of the pole. So now the position of the pole is depending on s squared plus 6s plus 9. So if you calculate the position of the poles, you have now the poles are at -3. Basically there are two poles, but both poles are at the same points. Sigma 1 and sigma 2, both of them are at -3. So if we plot them on the S plane, we have two poles at the same point at -3. So this is another category that is different from the three previous category. And the general solution, if you take the time to basically to calculate CS and then do partial fraction and then find CT, the general solution of CT will have the form of this form. It's equals to K1 exponential minus sigma 1t plus K2 t exponential minus sigma 1t, right? So we have only one sigma, well, two sigma, but they all at the same value of minus 3. So the minus 3 value is basically could be replaced in this minus sigma 1 that we have in this particular general solution. So if you plot this graph, what happened is we have something that looks like a first order time response, right? Something that looks like a first order time response, and you might think that it looks like the first and the second category, which are overdamped and system, and it might look like the first it might look like the first category, which is overdamped system, but this is not an overdamped system. This is basically the quickest response that you can get before going into undulations, right? So it still looks like first time response, but basically if you compare it to the overdamped system, so an overdamped system will be less faster, will be less responsive, but the formulas are the same. So basically this is a critical point, critically damped, where if you increase basically if the position of the poles change a bit. What does it mean to change? When the position of, so because now the position of the poles are at the same point, if you have them separated into two different points, what you will have is you have the overdamped, right? But if you start to separate them in j omega direction, you start to have the underdamped, right? So this is basically the sweet point between overdamped and underdamped. It's the critical point between overdamped before going into the underdamped. So that's why we call it as critically damped system. So the general solution, you can take directly the general solution is basically in this form, in this red rectangle. So if we were to summarize the four criteria, so here we can see the four criteria. The first one that we have seen is basically the overdamped system. So the overdamped system is characterized by its position of the poles. We'll see later. So the characteristics of these categories are defined by the position of the poles. So different position of the poles will give different time response. The first one that we have seen is the overdamped system, and then we have seen the second one, the underdamped system, and after that, not underdamped. After that, we have seen after overdamped, we have seen the underdamped, and then the third one is undamped, and then finally we've seen the critically damped, right? So let's look at the summary. For an overdamped system, it is a system when we have two different poles at sigma axis. When we have two different poles, real poles at sigma axis, you will have an overdamped response, time response. So it's a response that is very, very slow, but it doesn't have any undulations, right? The decay is very, very high because sigma axis represents the decay. So it decays, it goes directly to a finite value, steady state value. It has no j omega components at all, right? It has no j omega components at all, but the inconvenience is that it is quite slow. And then so for overdamped system, poles are real and distinct. That's what we call pole are reals. They are both on sigma axis and they are at different points. They are distinct. So that's the overdamped system. And then second one that we have seen is the underdamped system. So where is the position of the poles when we have the underdamped system? An underdamped system is when we have the position of the poles with real and imaginary component. We have both of them, real and imaginary component, right? Like this. So if we have an underdamped system, we would have this type of response, right? It also has a decay. It goes to a finite value at the end, but before going into the finite value, it has something that we call overshoot. It overshoots the finite value before going back to the steady state, right? It overshoots. It goes across the level of the finite value before decaying into that state. So it has two components. It has a certain undulation here, the overshoot, which is represented by the imaginary part, and it also has a decay component. So it decays to finite value. Decay component represented by the real component of the poles. So it has the poles are real and imaginary. And then the next one that we have seen is undamped system. What is undamped system? An undamped system is a system when you try to find out the poles. The poles are both of them imaginary or complex number. Both of them are situated on the complex axis j omega. It has no decay. What does it mean to has no decay? If you have no decay, then you have an undamped system where the system keeps on oscillating without any finite steady state value, right? So there are no decay at all, but you have an oscillation with omega of this omega that being presented in the pole. So for example, here it's 3. So that's for an undamped system. And finally, we have seen critically damped system. So what is critically damped system? Critically damped system is a system when you have both poles are real and repeated, they are at the same point, they are not distinct. When you are at such a situation, basically you will have a time response that looks like this. So it's the time response that's in the middle of, between overdamped and underdamped. So it is basically the critical point between overdamped and underdamped, right? So both poles are at the same real axis. There are two poles, but both of them are at the real axis at the same point. So if we look here, basically we can move the poles to get, if we change the transfer function, it means if we change, basically how do you change the transfer function? We change the transfer function by changing the parameters of your system. So for example, the parameters of the system could be in, let's take an example of a mass and then spring damper system, right? So you have parameters K, parameters D, damper, and parameters M of the mass. So this M, K, and D define the position of the poles. Basically, it defines your transfer function, right? Therefore, it defines the position of your poles. If you change M, D, and K, the position of your poles also changes. The position of your poles also changes. So how does it change? It can fall into these four categories, either overdamped, underdamped, undamped, or critically damped. So when you design a system, for example, this damping system, if you want the system to respond, if you want the system to respond without any ondulation, you should choose, for example, overdamp or undamped, overdamp or critically damped response, right? So in order to be in overdamped or critically damped system, you should have your poles always on sigma axis. So basically that's how a control engineer design their system. They will have a specification, and the specification will tell that whether they could have ondulation or they could not have ondulation, how fast the system need to be. So if they have those requirements, they will design their system, means deciding on their parameters of M, K and D, so that their poles will fall into one of these four categories, right? So now we have seen all the categories of second order time response, and we know that the type of time response, or the category, what we call category of or type of second order time response, depends on the position of their poles. So it depends on the position of the poles. So now a simple exercise that we're going to do here is, what we're going to do is we try to manipulate, or we try to play a bit with the position of the poles, change the position of the poles in order to see its consequence on the type or on the category of the time response. So then again, how do we change the position of the poles? As I've said just now, the position of the poles can only be changed if you change basically the parameters of your system. So let's start, if for example, if we have our poles in this position, right? So we have two distinct poles, which both of them are reals, and we know if both of them are reals, what we can do is that we can say that it has because the sigma axis represent the decay, so it has decay, but it has no ondulation, because both poles are basically, if you write them in, so let's say I call this pole as sigma 1 and sigma 2. Sigma 1 and sigma 2, both of them only have a real component, real 1 and real 2, and the real are at -7 and at -1. So the j component are 0 plus j0 plus j0. So there are no ondulations. So zero ondulation, only decay, no ondulation. So what happens is, when you only have decay and no ondulation, you'll see a response that looks like a first order time response. So that's what we call an overdamped system, right? So now what do we do? So let's imagine that what we're going to try to do now is that we will change the value of the poles so that they got closer and closer with each other. They got closer and closer. So instead of having, for example, -7 and -1, we would have it now, we'll move into both of them at -3. It's a point somewhere in the middle. So in this position, what you have is that you will have a critically damped system. What is a critically damped system? Critically damped system is a system that still don't have any ondulations, right? Because we see that j omega component, because sigma 1 equals to -3, sigma 2 equals to -3. So -3 are basically, these are the real components. It has j0 or zero component in the ondulation part, in the j omega axis. So there is still no ondulations. But what will happen is that the system will get faster. The system will get more responsive, what we call more responsive. So it is much faster than an overdamped system. So otherwise, that's why it's called overdamped. You put too much damping on the system in an overdamped system, that it is not as responsive as it should be. Now in yellow, what we have is a critically damped system. It has a just nice value of damping, so that it can respond quick, but not yet having any ondulation or vibration, any ondulation, right? So that's the effect when we move. So previously the poles were here, it is overdamped. We move it closer until it becomes at the same point. We have a critically damped. So now that both of them are at the same point, let me change color now. What happened if once they are at the same point, what I can do is I can add now a j omega component. So that's what we have here. We were at this point and now we add j omega component. Right? So now poles sigma 1 and sigma 2, it has the same value of real component. Right? Both of them are here. For example, it could be here equals to -3, but they have different value of j omega. One is at j square root of 8, another one is j minus j square root of 8. So one is on top, one is on the bottom of the S plate. So what we see now is that it has a real component and it also have a complex component. Again, what does real component represent? Sigma part or real component represents the decay, whereas the j omega part represents the ondulation or sine wave, or you might call it as a vibration as well, ondulation. So now it has both. It has decay and it has ondulation. So what is the decay? Decay is basically it's an envelope that represent the signals. So you will have something that looks like this now. So from the yellow signals, now it has become the green signals. So it is faster, of course. You can see that it increased to the value of the steady state faster with a smaller t, but it has what we call an overshoot. It overshoots the steady state value and it ondulates. So now we become underdamped. Likewise, that's why it called underdamped, because we don't have enough damping to attenuate the ondulation. So we can see the ondulation, but still it at the end it will have a decay and it goes to a steady state finite value. So now what we can do next? So we have tried 3 variation of position of poles. At first it was different but real. We take it closer to become real but at the same point, and then it's not just real, it also have real components and complex number. So next, what we can do next is, let me change color now. What we can do next is try to move these 2 points closer to the j omega axis, or sigma equals to 0. So now it was previously in underdamped, it was here. When we move it here, what does it mean to move it here? It means that previously we have a real value. Now we decrease the real value until the real value becomes 0. So now we have both poles sigma 1 and sigma 2 with 0 real part, and it only have the I wouldn't put it like this. So it will only have the complex component. I'm sorry. So it doesn't have any real component. It only have complex component. So again, the real component or sigma component represents decay. The j omega component represents ondulation. So when we have it equals to 0, it means we have 0 decay, no decay. What we only have is we have only ondulation. So what signals have only ondulation without decay? So basically it is sine or cosine wave. So that's why at the end, if we move or we change the pole's position to become in this position, what we'll have at the end is that we will have a purely sine wave. And now it is what we call an undamped system. So it is not a damped system anymore. It doesn't goes toward a final steady state value. It has an average value, but the value keeps on oscillating like a sine wave. So this is what we call an undamped system. So there you go, the variation or the four types or the 4 categories of second order time response, right? The overdamped, critically damped, underdamped, and undamped system, and they all depends on the position of the poles. And the position of the poles, by now, these 4 position of the poles. When you do your exercises or you do your problems, when you try to find, when you find the position of the poles, you can directly say that the system is either overdamped, critically damped, underdamped, or undamped, without having to go through all the calculations of partial fraction, inverse Laplace, and find the exact equation of a time response, right? So having studied all the time response, all the criteria and types of time response second order system, we can now try to do several exercises and examples. So let's take these particular examples where we have a transfer function of 200 over s squared plus 10s plus 200. So what should you do first? In order to estimate or evaluate the time response, as usual, the steps are, the first one is to find the poles. So to find the poles, the equation that you use to find the poles is basically solving, finding roots of the polynomials over here. It is a second order polynomial, so we can use this equation, this formula. So we found out that by using this formula, so you can either use this formula, calculate it by hand, or if you have your calculator, it will be much quicker. You can use your calculator, and then you'll find that you have two different poles, sigma 1 and sigma 2, at -5 plus minus j 13.23. -5 plus minus j 13.23. So what do we see here? We see that we have two poles, and both poles have the two components of real number and complex number. Real number representing the decay, so we have decay at -5, so it's a decay from a high value decreasing towards a finite value. And now here in this part we have a pulsation, which will be represented by an undulation on the time response. So what type of response is this? So please look back at the lecture and find out what type of response it is. If you look at it, what it is basically it is an underdamped system, right? It is an underdamped system. It is a system that decay, but it still has ondulation, so it is underdamped system. So an underdamped system is a system that have poles, two poles with both a real and imaginary component. So the general solution, you can use directly the general solution of an underdamped system that you can find in the slide that I have presented previously. So the general solution is in the form of Ct AE minus sigma dt cosinus omega d minus phi. So basically we have the exponential component here, exponential minus sigma d, and we have the ondulation or the j omega component over here represented by cosinus cosine wave here, cosinus omega d minus phi. So we don't have to find, basically it is just an estimation. It is evaluation of time response by just by inspection. So if you need to find further the exact value of a and phi, we can do that, but for the moment what we're going to do is just from the transfer function estimate what type of second order time response it is. So now it is an underdamped, and we have this kind of general solution. So in the same equation you have the exponent part, which represent the decay, and we have the cosine part that represent the ondulation. So if we replace the value, we have sigma d, which is our sigma in real component, which is -5, and then we have the omega d that we have found here, the j omega components, it is equals to 13.23. So this is the general solution. This is our particular solution with our poles, right? So if we plot it, it is an underdamped time response, where it has an exponential decay of -5 and it has an ondulations of 13.23. So we have other examples as well. So I'll let you do all the exercises in order for you to be familiarized with the concept of types of second order response related to their poles position. So now let's try this one. So it is a transfer function of gs equals to 2 over s plus 2. What are poles and what are zeros? So let's do this together. So what is the poles? So the pole is basically we have to look at the denominator. It's the value of s that turns the denominator equals to 0, right? So that's the value of poles. So the poles is basically, we have only one poles, sigma 1 equals to minus 2. So we know that the polynomial that we have here is a first order polynomial. So this is not a second order time response. We will have a first order time response. We will have a first order time response. So as a first order time response, so the first thing, we'll do it point by point. So the first one is ask what are the poles and what are the zeros. So the poles is minus 2. What are the zeros? Do we have any zeros here? Zeros is basically the term of s that will turn the transfer functions 0. So there is no zeros basically. So there is zeros. There is no zeros at all. Second question. Let's plot the poles and zeros on S-plane. So S-plane. So S-plane is the two-dimensional plane with the two axes of sigma and j omega, and we will plot the position of the poles and zero. So our poles is sigma 1 equals to minus 2, so it is somewhere over here. So sigma 1 equals to minus 2. And then the third question, write the general expression of the step response. So it's the general expression of the time response basically. Step response, time response can also be called as step response. Why? Because every time we want to find a time response, the typical input transfer function that you put is a step. So we can also call it as a step response. Right? So the output of a step response is also called a step response or time response. So what is the general expression of the step response? So this is a first order time response. You can go back to the lecture that we've seen during last week. So the solution, the general solution for a first order time response will be equal to Ct equals to 1 minus exponential minus At, with A being the poles. So what is the value of A now? A is minus 2. So our time response will be equals to Ct equals to 1 minus exponential minus 2 minus 2t, right? Minus exponential minus 2t. So this is our time response. I'm sorry, it's not minus 2t, it's 2t, because A is minus 2. Okay, and then next it asks for the state, the nature of the response. State the nature of the response. So what is the nature of the response? When we ask for the nature of the response, so I'm gonna write, it's a bit everywhere, but I think you can get it. So when we ask for the nature of the response, is two things. State the type of it. So this is a first order time response. And the second nature is to tell whether it's stable or unstable. So now in the first order time response, we know that for this particular equation of time response, it will be something that looks like this, right? And it will have a steady state value. So it is a first order time response which is stable. So that's for this first example. Now we have the next exercise and the next example. Right, so let's do this together as well. So we have 4 questions, same as in the previous slide. The first question, what are poles and zeros of our system? So what are the poles? Poles, it's easy. So we have one here, one over here, 2 poles. So the poles are, we have 2 poles, and the poles are sigma 1 equals to minus 3. Sigma 2 equals to minus 6. Why? Because it's the value that will turn the denominator equals to 0, or the transfer function into infinity. So these are the value of the poles of our system. Second one, plot our poles and zeros on S-plane. So again, I forgot about zeros. So there are 2 poles. What about zeros? There are no zeros, because there are no value of s that could make this transfer function becomes zeros, because there are no s on top of this transfer function. Okay, so now next question, plot on S-plane. So again, S-plane is this two-dimensional plane of sigma and j omega. So our poles, both of them only have real components at -3 and -6, so they are at here -3 and -6. So -3 being pole number 1, sigma 1, sigma -6 being sigma 2, pole number 2. So this is our plot of poles on S-planes. Okay, now we go to the next question. Write the general expression of the step response. So the general expression of the step response. Which type of response, second order response is this? We know that it is a second order time response, but which type is it? The type that have two distinct real poles. So in order to if you have to guess, well, basically if you have both of them at real poles, at real axis, no j omega values, it means it has no undulation. So we know that there is no undulation. No undulation means it could be either two choice. There's only two choice without undulation. It could be either overdamped, where you have too much damping, no undulation, or critically damped. So which one among this is it? Is it overdamped or critically damped? So if you look into the slides, previous slides, we know that if the points are distinct, we are basically in the case of overdamped. If the points are at the same points, we are in the case of critically damped. So now we are in the case of overdamped. So if you look back into the slide of overdamped response, what is the general expression of an overdamped response? The general expression would be, if I write down here, so the general expression of the time response Ct of an overdamped response would be equals to K1 minus K1 exponential minus sigma 1t minus K3 exponential minus sigma 2t. So it is an overdamped response. So this is the general expression. So of course you have to replace sigma 1 with the value -3 and -6. So here sigma 1 is equals to -3, sigma 2 equals to -6. Okay, fourth question. State the nature of the response. So what is the nature of the response? Again, there's two things that you need to respond. The first one is on the type of the response. So which type of response is this? It is an overdamped response. So the nature is it is overdamped. It has an undulation. It is an overdamped response. Yet it is overdamped, but still it is a stable system. Why? If you plot the graph, basically it is overdamped. It means it has no undulation, and it goes towards a steady state, a stable value. Overdamped response means no undulation. Okay, so that is for example or exercise number 2. So I encourage you to do the next one as well. So in this exercise, let's do this together again. So the same thing, we have 4 questions, the same question. The first one is to tell what are the poles and the zeros. We'll go through this very quickly. So the poles, how many poles do we have? We have 2 poles at -10 and -20. So sigma 1 equals to -10, sigma 2 equals to -20, right? And then what are the zeros? Now we have a zeros. What is zeros? Zeros is at -7. Plot it on S-plane. Okay, now plot it on S-plane. Let's plot together. So we have sigma j omega. We have -20 sigma 2, and we have -10 at -10 sigma 1, and we have 0. So we have to plot zeros. If you plot poles by marking X, for plotting zeros, you will mark S as round, a circle. So at -7, you have the zeros. So we've settled these 2 questions. Write the general expression of the step response. What kind of step response is this? Of course, there's a difference now. There's a small difference now that we have a 0. Previously we didn't have 0, but does it influence in any way the step response? No. Why? Because the step response depends strongly on poles, and the poles are basically two distinct points, right? Two distinct points, and both of them are real numbers, so no undulation. If you have no undulation, it means again it's either 2, whether an overdamped system or a critically damped system. And we know if we have two distinct points, it is basically an overdamped system. So I'll let you continue. If it is overdamped system, what is therefore the general expression, and what is the nature of the response? So I think you get the idea of the exercise now. Each time that you find a transfer function like this, be it in first order or second order, you can do, the first one is what you can do is find the poles and zeros, plot it on S-plane, and from the plot on S-planes you can deduce the general expression and the nature of the response. So this is another exercise with another polynomial over here. You would find different poles position. I don't know, try to calculate it. You might have now a j omega component, therefore another type of response. So try to do this and answer all the question. Same goes for here. So now you have another polynomial here that would lead you to another type of response. And then again, please try to do this as well. This is another exercise to be done. So now we are at the end of the lecture. So we have covered all the things that we need to cover this week. So by now I hope that you are able to determine the time response of a second order system using the poles and zeros that you extract from the transfer function. So please do the quiz that I will attach with this lecture notes in your Google Classroom, and until then I'll see you next week with another chapter. Thank you.